the more complex the model will be. And at the end, I can classify each single point. If I limit the level down, I will reduce the complexity. If I limit or increase the number of trees that I use in the ensemble, I will average similarly to the KNN, because it's an average vote over all these trees. And the majority wins. This is a way to flatten out, to smoothen out. So this one, the number of trees in an ensemble that are used would reduce complexity because you make an average vote over all these trees. Similarly, this one, if I limit the number of leaves, the number of splits, okay, I control the complexity and say, I don't allow in any tree more than 20 splits. Zack. Then you have to stop. Huh? Probably it's not finished then because you didn't classify all the things correctly, but the next random forest, which takes different features, might do it correctly. So this is a way to control the complexity. Huh? And number of leaves, number of levels, here the complexity, if I increase that, actually complexity goes up, variance goes up. Here it's the other way around, variance goes down because it's an average. And probably the last one to stop then, you have heard of support vector machines, right? There's also a parameter there as a hyperparameter. Do you remember which one this was? Support vector machines. Now without a curl. Yeah? The C, right. What does the C describe?
Yeah, how much you want to analyze lines from different.
Right, exactly. Let's call it the C, or sometimes it's called the C tilde. And what we say if we increase the C, now we have to think about C or which word?
Depends how you define.
Right. Okay, you allow with a given C actually that there are misclassifications, right? The more misclassifications you allow, the more complexities in this model. No, the smoother it gets actually, the border, the smoother it gets. And one big thing that you have to remember with support vector machines actually is that there's always a maximum margin. In the definition of the optimization problem of the support vector machine, we demand that between the classes there's always a maximum margin, with some exceptions. And this maximum here, this one is max. This is a way to regularize it. There's only one way to put the border so that it's maximum. And so I throw away a lot of other possible borders. There's only one optimal. And that's why support vector machines are actually very gentle learners. They reduce intrinsically already the complexity. That's why they were also very famous because, or before the neural nets began to grow. This was state of the art before actually in the 90s. People learned how to train huge neural networks. Of course, we could also continue here with neural networks, but it's not really the topic of this lecture here. Also there you have ways to regularize, to reduce complexity. If you sum up in a convolutional layer and later in a pooling layer, just we take all these cells and just sum it up, and only the maximum goes out. Actually, this is also a way to reduce complexity. You spare or you save some parameters. So you see, all these learners, they have ways to control this complexity. Yes?
But it is correct if C is growing, so the variance is going down.
Right. Depending on the definition of the C. Look up how you did define it, right? And how scikit-learn defines it. Sometimes it's the inverse. 1 over C, C. Good. Okay. Cross-validation. Now we do it a little bit better. I know time is already over. We call this the inner loop and outer loop. The inner loop is used for hyperparameter tuning. For example, in a KNN loop, we would say, let's vary the number of next labels from 1 to 15. And then let's look how the performance is on the unseen test data. And we choose the 1K that gives the best performance. Exactly here, polynomial. Let's vary the order of the polynomial from 1 to 15. Let's take the best. Exactly here, let's vary the number of leaves. We don't know per se at the beginning, a priori, what's the best one. So let's find out. The machine can do it overnight. Okay, better than 2-fold is K-fold cross-validation. And normally 5-10-fold cross-validation is kind of an optimum. This is just an experience. It's not a theory. It's just comes out from experience on big data sets. 5-10-fold, and this means we do it this way, not split it into one training set, but we split the training set sequentially into different subsets. And if we say 5-fold cross-validation, we will take here, for example, 20% 80, and the next one, we leave that away, give it to the training data, and take part of the whole training data into the validation data. And if you do that manually, it's quite a lot of work, but fortunately, everything is already implemented in scikit-learn. CD cross-validation. And we can also get a cross-validated performance, just as we say, give me the cross-validated performance of this learner. Then intrinsically, it splits up the data into 5-10 subsamples and calculates the performance on each of these splits, averages the performance and gives only that one back. You can also get the whole array of these 10 tests, but normally you just look at the average over all of these data sets. Okay, how do we do that? It's another way to do it, and this is what I mean. This is a method that you should remember, cross-val score. Cross-validated score of any learner means you give the data, you give the target Y. Here it's the iris data set. It's these flowers, that you can classify with the length, the shape of the flower itself. And here you can say, okay, give me the cross-validated score of my classifier, CLF. It's an instance of any classifier. Could be a K and N classifier. Could be a support vector machine. And say, okay, give me a 5-fold cross-validated estimate of the performance. And then when you start that, it does a lot of work. It does split the whole thing, trains it, gets parameters, and evaluates. Here we have a support vector machine with a linear kernel, C equals 1, and then you get the scores. How good is it? What's the accuracy of this classifier? For example, precision, recall, F1 score. Here we have the F1 score, which is a weighted average or an average over the precision and the recall. This is really a good way to do, and it's in one line of code. Good. And then there's the last one, the leave one out, LOO or LOOC. This one is the one, if you have really few data points, then it's the best way to say, okay, I only leave one measurement point out. The rest I take for, in my training data, the rest I take for estimating my high performance. So you have to do it n times if n is the number of samples in your training data set. And this is really good. Just remember, leave one out. I will do if I have really few data points. Then I do it if I have 100 half the data points. I take 20 for the validation, 80. Then I do 80 times the training just with one sample list. Okay. Now there's another one which is stratified K-fold. This is to remember if you have uneven classes. So if the classes are unevenly distributed. We don't have, from every class, if we have 5 classes, we don't have 20% of every. And that's normally the case. That's also why it's called stratified. Stratified means in German geschichtet. It comes also from econometrics, actually, because our society is stratified. And if I want to predict the outcome of a vote, I have to take care, who are my voters? From which social layer do they come? and how much are represented from that layer. And so if you do an estimate of the outcome of the next vote, you have to take a sample that is stratified for Swiss people, for people living in Switzerland. Huh? You have to take old ones, you have to take young ones, you have to take women, you have to take everything. Huh? This is a stratified sample. And here it's just summarized these 5 steps. You split it first, then we teach the performance of either different learners. This is normally also the case, that you say it's not only one learner. Let's try all these things here. And this you can put in a pipeline. Duck, duck, duck. And within this pipeline, or a pipeline is enclosed in a grid search that controls these parameters. Huh? So it's a loop in a loop. And at the end you test everything fully automatically and look at the performance, and then you take the one learner that gets the best performance using the best parameters for this learner. Okay. Yeah, and then you can deploy it. It's called deploy. Then you can sell it. You can go out and say, I make a homepage where I can predict the next outcome of the vote for anything, or for Switzerland. Now I think it's time for a break. 5 minutes break, then we continue. It's okay? 5 is okay? Here's an example of the grid search over one single parameter. I take again the polynomial, because I think it's so intuitive. We just increase the order of the polynomial here. We make a pipeline, linear regression of the generating these polynomial features, and then we generate something like, it's called a validation curve. This is just the performance as function of this hyperparameter. This is called validation curve. We will also calculate the learning curve. This here, a validation curve goes over the hyperparameters that have to be optimized. And it would look like this, for example. The degree, given some data set of the polynomial, goes up to order 20. And then we see, okay, the mean squared error goes down for the training data, it continues to go down. But at some point here, you see that now the validation error, the cross-validated error goes up. And you lose again, because the variance gets bigger. The variance of this error, here, the variance part, gets bigger and bigger and bigger. It's an overfitting here. I would stop somewhere here, I would say, about 5, 6, for example. And then you would say, this is probably the best parameters that I can get for a polynomial feature. And this you can do with every hyperparameter of every learner. And then it's called a validation curve. Just graphically displaying a score means a performance measure or an error measure, which is one minus the one, or the reciprocal value of that. Then you see how this behaves.
This is correct that you do a cross-validation over tests at the...
Yeah, right. And here I've just listed what are possible values that you can display in a validation curve. Plenty of scores, and you have to decide yourself, given the application, okay, what score is the best for me? Or shall I display just the mean squared error? And you see also that some scores are not applicable to all other learners, because some are specific for a classifier, like a recaller. This you kind of use actually for a regressor. But you can just get the list of scoring functions that are available that you can look for in scikit-learn to use it in a validation curve and display all these scores. So the way to judge how good a learner is depends on the application. You have to select one score. Okay, grid search. This is also what we do. A grid search consists of an estimator, a parameter space. This is actually the grid where we say, let's move vary k from 1 to 5. This is the parameter space for the k and n. And this we normally define in a list. It's actually brackets or in a dictionary in Python. And we give actually our grid search instance, we just give these grid parameters, and then it will automatically loop over all combinations of these grid parameters. A lot of work, and then you also will see that your computer gets warm to do that. And one idea is here. You see, what do? We call grid search cross-validated grid search. So this is the double loop inside here. So we do a 5-fold cross-validation, and we do a grid search over certain parameters. Here we have, for a support vector machine, we choose different kernels, either a linear kernel or a radial basis function, the kernel. And then we select our scene, sexy parameter with scene, in 2 values only, 1 to 10, or 1 and 10. If you want to have more, you just list them up. With this dictionary, you go into the grid search, and then it will evaluate all parameters cross-validated over this data you have using all combinations of these parameters. So you get a huge list at the end, and what you then can put is actually you get a sorted list out of the best parameters, or you also can just choose best, and then you get the best combination of all parameters. Then you know, within my hypothesis space, this is actually a hypothesis space for different learners that you parameterize now in the dictionary. Within that hypothesis space, the best one is this and this, the best possible learner from the learners that I tested. Okay. We have seen validation curves, now we go to learning curves. And the big difference between validation curves and learning curves is this. We don't display it as function of a hyperparameter, but as function of the training set number of elements, the set size of our training samples. And if we increase that, actually, you can imagine that normally, actually, the model can display more and more complexity, and so can also, or the data can also show more and more complexity. And the model might adapt better or worse onto this higher number of samples. With this, you can split until you get to the edge of your 80% of the data set, and then you have to stop. You don't have more data, and the problem is often that even this data is not enough to really say what should happen next. Or at least you can say, I should need more data. And then there are the following things that can happen. The accuracy. So you always have to look at what is on the y-axis. Either it's an error, then the whole thing will be flipped, or it's an accuracy. We want to attain high accuracy. So our goal is 90% accuracy on training data, on test data. If you see that one, that a learner actually fails to get this high accuracy as well on the training as also on the test data, then we say, this learner has a high bias. It cannot learn what we want. It is too simple. Both actually converge to a certain error, so the gap is small, but the accuracy is bad for both data sets. This is a learner with high bias. Yeah?
If you have such a saturation function for the accuracy, you learn to calculate how this function would go for a larger set. Is it?
If you're saturated, no, then you're fine actually. Yeah? Huh? For example, here, the gap indicates how big my variance on the model is. We have good accuracy on both things.
I just wonder if you have to start and you don't have a lot of samples, and then you want to predict whether you reach the goal you want to have, given the accuracy from lower samples. Does it actually work? Or is it?
Yeah, how to extrapolate? You want to extrapolate the curve? No, it doesn't really work. No. I think you have to go until it's really more or less asymptotic, or it deviates again. So extrapolation, you can, for example, say, what will happen with more data? It could be that it stays like that. it's not necessary that it converges to this line which is indicated here. So actually here we would need more data, for example, because we have actually, okay, with training data, we would even get better with more data, and probably also better with the test data. With the training data, the test data, validation data, but we still have some variance here. The gap indicates the variance, but the bias is not bad because we finally achieve a very good accuracy on the training data. And so analyzing these curves gives you a clue what to do next, or to judge what is the problem of my estimator, of my learner. Do I have a high bias problem? Do I have a high variance problem? Or do I have achieved actually what I want? And achieved means actually I want to attain a given level of accuracy which is given by the application that I want to fulfill. This we will do in the exercises for different learners, cross-validated. Important is here, this is not just one snapshot of one test, that is all cross-validated data. So with these curves you can even give a variance onto this data, the uncertainty of this estimation. And then you see if the uncertainty is big, this is probably another explanation for your question. We would also plot the uncertainty of the estimation of our accuracy. Then we see if it big, then I have to do something more. Okay, the idea is again here with a polynomial, we would say we increase the number of samples, either it's training or test samples. With 1 point I get a perfect fit, even with a simple model. So the accuracy is really small here on the test data, but for example the next data point would not match. The test accuracy would be worse or really bad. As I add more data, the model still on our curve second order, actually it's not a perfect match now, even on the test data, but we also get a better accuracy now on the training data. But these curves then converge at a given level. Training data achieves here, and the error, here, what is it big? Is it big? It's small? It depends on the application. Depends on the scale here, and on the requirements of my application. But generally, if the gap's small, we can say small variation. We don't have a zigzag curve around these points here. It's quite smooth, I would expect, okay? But error is still here. It's the sum of these squared differences from the curve. Yeah, it's a given level. Now, if you have a high bias, we would fit, for example, a straight line to a curved curve. And then we could something like that. We won't get an error which is smaller than the differences of all these squares. So we cannot be better than that. This is the level of that one. But the variance is small. Also for new data points, it's unchanged. If I put data points here, because the model or the real data are supposed to be distributed around these points, it's the same error. So they will converge, but they have a high bias. That's a high bias. Okay, and now we have the problem of overfitting, which we can control, which we'll see by regulation. Overfitting manifests itself by this big gap. Means actually our estimation of the model looks like this Wiggin curve, but the real data set is actually more or less on that curve. And then adding more data points into the test data set, we would see, okay, there are big errors now get generated because actually it doesn't match really what we have. And then when you see such a big gap, it's called, we have an overfitting problem. Complexity of the model is too high, the data does not show this high complexity. It doesn't show these high frequencies. It's much simpler actually. Then we should stay simple with this model. Okay. Here is actually a little bit a hands-on summary, what you can do if you look at these learning curves. Suppose you're using some algorithm on a given training data set, but it makes unexactly large errors. The first thing is, what nature are these errors? Is it high bias? Is it variance? Is it both? Or is it just that my model is somehow totally wrong here? What should be tried at? Sometimes getting more training data helps. But training data is expensive. Normally means measuring again. Often. With more data, we can control this overfitting problem. The overfitting. We can also reduce the number of features. This is also a way to reduce the model complexity. Like in polynomial features, we reduce the order. We reduce, for example, the number of features disclosed in one random forest. So we can say, okay, we have an input data set of 50 parameters or 50 feature vectors. We don't need all. We take the most important ones. There's this technique called feature selection, which we will look next time, to select really good features. If we have the other way problem, if we have high bias, we should generate new features. So we can combine features out of the existing ones, like we make a square, we put a kernel onto that, we go to higher dimensions, support button machine which goes into a high dimensional space using the kernel trick actually does this. It adds complexity. Polynomial features I had said, and now comes this lambda. Now what is this lambda? This is now the knob to control complexity over regularization. And regularization is a penalty that we add to the goal we want to achieve. On the one side, we want to minimize the error. On the other side, we want the model to be as simple as possible. Means actually to reduce the number of necessary parameters in that model as big as we can, as much as we can. And then we get this, we'll do together here, kind of these learning curves. For example, here we have our k-nearest neighbor classifier. And we will analyze this for each one for yourself and try to find out, okay, what is the problem here? We have here on the training set accuracy 1. On the test set, it goes up. Here we have how many neighbors? 32 neighbors. It's quite smooth. Okay, this we have. Now we go to the knob of regularization. Imagine it's like on a hi-fi sound machine, the knob where we can control continuously the complexity of a model. How is this done? This lambda parameter is now an additional hyperparameter that we add to say, okay, if we have a complex model, I can tune up the lambda, and then it gets simpler. It's less complex. How is it achieved? This is called regularization. Normally, we minimize a loss function. Machine learning is always defining a loss and minimize it. Either analytically to manage or mostly numerically by gradient search. But defining the loss itself is not the best thing to do, because then you always have the problem of bias-variance trade-off. We look for the parameter set that minimizes the loss, here with the argument. Now, this fits the data perfectly. Our training data, probably not our test data. Now we make a trade-off, and we add, with a given parameter lambda here, a penalty term. It's called the regularization term, R. How does it look like? And yeah, it's a little bit difficult, but this one should represent the model complexity. The bigger R is, the complexer the model. Now for a polynomial, we could just count the order and say, okay, this is lambda times n, where n is the order. Would be a way to do it. And we will limit it, but there's a better way to do it. We just take the norm of our parameters, the length of the vector of the parameters. And we say, you should limit, actually, the parameters. You can distribute your weights, but you can distribute only a weight in summa from 1. You have to separate it out. Then you have to choose the best parameters, but you only can separate it out once and limit it. This is the penalizer of complex models, the regularization parameter. And with this lambda, this is a continuous one, another hyperparameter, so we add a little bit of complexity, but at the end we reduce it, and this lambda controls continuously the model complexity. And how does it work? We add to this loss function here, for example, for a polynomial fit, this would be our feature space up to order P. Now we want to say, we want to automatically select the best P out of this. We could do this by a learning curve, or a validation curve better, and say, let's vary P, and then we look at the errors on the training and the test data set. But there's a better way to do it, and I just tell it here. We add a penalty which weights the parameters of this polynomial, and the bigger these parameters get, the less, actually, the less on the parameter lambda, minus lambda, the bigger my error itself gets. And there are two ways to do it. Either we do it by the 2 norm, we square all these parameters up, and there we have a smooth norm, or we do it by the L1 norm, which is the absolute value of each component, the sum of it. So this is called the Euclidean norm, and this is, for example, also called the L1 or Manhattan norm, which takes the absolute value of each parameter of the parameter vector. Okay, and this one has one big advantage. This one puts some parameters to 0, and that's actually what we want. In a polynomial, for example, you could say that the fifth power gets 0. The parameter for the 5th power gets 0. And that's what we want. Then we just neglect this feature vector. X to the power of 5 can then be 0. Here we can leave it out. But then we have reduced the complexity. And I go just a little bit further. I miss one slide. Sorry, here we have the lambda. The bigger the norm gets, the worse it is for the theta. But I think it will come. How can we understand that? Normally we have to optimize here. We have to find the minimum of our loss function, And normally this loss function is not that smooth as it looks like, but here we have a good situation. We have actually one dedicated minimum. In case of a linear regression, there's only one minimum, and we can find it over the normal equations, and there will be a θ1 optimum, a θ2 optimum. Now what does this regularization do? We say the norm of θ is limited, and the norm of θ is the sum of the squares of all components. And this is a hypersphere. x1 squared plus x2 squared plus x3 squared is equal, let's say, to 1. This gives a ball, a sphere in a p-dimensional space. And we say this is limited. All θ parameters must be within this sphere. Now we have to find the optimum of the loss, given that θ cannot be bigger than that one. And then we have to find, okay, the optimum will be here, but we limited actually the weights of our parameters, and the best thing will be here. So we have limited our θ's. The optimum θ's are much bigger, and we shrink them. So the model has to decide which one is really more important, and gives the weight accordingly. With the L1 norm, if we say, for example, the L1 norm of a vector x and y is just x plus y. If we limit the L1 norm to 1, we get this equation. And this equation has the following solution, this here. This is a diamond which goes to 1, 1, minus 1, minus 1. This is what we do with our estimation parameters. We limit it kind of in this diamond. And the nice thing of the diamond is it has edges. And the best solution will normally be found on some edges. For example, here. And what happens on the edges? On one edge, the other parameters are 0, or some of the other parameters are 0. And here we see θ1 is equal to 0, means that the feature 1, x1, gets out. We don't need it anymore, and everything is on the weight of theta 2. This is a way for feature selection. Huh? We can minimize now the complexity by the lasso regression, yeah? Because we know it kicks out some parameters. It brings them to 0 because the combined optimization problem is such that the optimal will be found on, it's called this norm ball, although it's not a ball, on this norm diamond. That's why L1 regression or L1 regularization is a good way to kick out features. It's a way to use it for feature selection. And then, because machine learning is always also a little bit trying out, it would be a combination of the two. This one is just that you know it. It's called elastic net, because we elastically connect this norm with this one and get something like that. And it's a compromise between the two. And whether now a lasso regression, a ridge regression, or an elastic net regression is the best, you have to try out. You have to try out in a grid search. I say, okay, let's regularize it. We put a lambda parameter. The lambda is varied from there to there. And we use for the regularization function, we use once the L1 norm, L2 norm, or a combination of them. This L1 norm is a, you know what it is? L1, L2? Not really. Okay. So, this is a Euclidean vector V. Yes, let's say a component Vx and Vy. The length of the vector in a Euclidean norm we would write like this. It's the Euclidean norm is phi x squared plus phi y squared square root. This is Euclidean. Now we can also say that's the Manhattan norm. If you are in Manhattan here, and you know, okay, the streets go like this, and from west to east, you cannot take a path which directly goes here. You have to take this way. And this way is given by the L1 norm. And then we would say, from this vector, the L1 norm is phi x plus phi y. And this one goes around the blocks of the Manhattan. It just counts actually the sum of all parameters. And it's exactly the difference. This is an actual one, it's bigger than one. And the general LP norm is then defined as, okay, sum of the vector components E to the power of P, and then the square root of P, or the root of P. That's the LP norm. Huh? And we normally only use 1 and 2, and then there's another one. When P is infinity, then it gets to the maximum component. Huh? So when we limit it, or when we make the transition to P equals infinity, we get the maximum component of the vector, because all others, they get 0, and only the biggest survives. That's the norm, and these norms are quite important in terms of optimization. It defines actually how my airspace looks like. Okay, I think, do we have some minutes, right? Well, it's 2:45, that stops, right? Okay. Now, when you make a complicated error function which has some regularization on, let's see the L1 norm regularization, regression, then we don't find anymore an analytic solution for this one. Then we have to go to numerical optimization. And numerical optimization is normally done using a gradient search. Did you ever hear of that? A gradient descent? But you say, okay, you're on a mountain, you're on the Uetliberg, and you look for the quickest way down. You want to go to the lake, you want to have a bath down. Which way do I take? You calculate the gradient of the Uetliberg on the point that you are. Then you take the negative of it. Then you know this is the quickest direction down. You make a step eta in that direction, and you do it again. The gradient shows in a little bit different points in a little bit different direction, and then you switch to that one, take the negative gradient, because the gradient always points up to the mountain, you go down, another step. And you stop only when the gradient gets flat, and then it gets 0, and then you know, okay, I'm at least in a local minimum. And that's what's shown here. If with an L1 penalty, these normal balls, they are edgy, and also the optimizer, when it does a gradient descent, actually will stitch to the edges. And what we see is also here that theta 2 gets 0, while in a ridge regression with a smooth normal that has no edges, it will find just a compromise. Yeah, let's say, okay, I give a little bit more weight to theta 1, and a little bit less to theta 2, but it will never kick out one of these parameters. Just say, okay, I'm smooth, I don't want to quarrel with you, but L1 is quite hard. You're out, zack. The other one is not. Okay, now let's continue. So, regularization is one way to reduce model complexity. It avoids overfitting, and we can do this with a parameter lambda and control in a grid search. This is shortly the thing which is there. And I was looking for this transparency. Here's again shown, okay, we have the mean squared error, no, it's the total error plus lambda, and as bigger as theta gets, my parameters of the model, the bigger actually is my error. And it tries to minimize both. So to minimize this one, actually the entries of this vector have to be small. And here as well. This one can be solved analytically, this one not. Here we use gradient descent. Gradient descent. And this is shown here. This is going down the Uetliberg, calculating the gradient. And what gradient? Of course, not the gradient on the Uetliberg. The gradient, our Uetliberg is the loss function. And we want to get a minimum error, a minimum loss. We have to take the gradient of the loss function over the parameters. All partial derivative. This is the step size. Sometimes also called learning rate, and we take actually an approximate, an iterative way to say the next parameter is the old one plus a step in that direction, until we get an almost vanishing gradient, which is 0, where we see, okay, now it doesn't change anymore. Then we stop here. Normally in a local minimum. The gradient here can be calculated analytically, shown here. But for the L1 regression, we cannot do it, so we have to go for numerics. This is the summary of today, actually. The idea is to start with a low bias algorithm, so high complexity. Feed it tons of data if you have, and then you get at least look for a small test error. Then it's better to start first with the simple algorithms, before you then go for higher complexity. It's probably better you start from the lower side with a high bias and add complexity later. Try different algorithms. It's a good practice also. Do it in a grid search. Always use cross-validated performance measures. If you still have problems with overfitting, try regularization. Add a penalty term that penalizes too complex model. Using learning curves, you can check what the problem of your learner is. Does it suffer from high bias? Does it suffer from high variance or both? And then you can deduce what you can do. Okay, Do I have to add more complexity? Do I have to give the model more parameters? Do I need more trees, for example? And sometimes, if more data is labeled, you can also augment the data. You can artificially create data out of the data you have by combining these, for example. Or in an image, this is normally done. If you have an image of something and your classification is based on images, you can flip them, you can shift them, you can change the colors, you can add noise. These add samples that you can use, and it adds robustness to your model. So it's not always necessary that every picture is taken manually. You can also generate new ones from a process that normally occurs also in nature, right? It's moved a little. That was very noisy. The sun was shining very hard. And then you can reproduce these kind of processes to generate new data. It's a good way. Okay. Yeah, sometimes the covariance shift, just as a reminder at the end, is sometimes you train a model on test data that is 1 year old. For example, you want to predict the failure of a machine, and you have taken a lot of parameters like vibration and sound of the machine, and you apply it just the year after. And probably a lot has changed since then. And the training data that you had from the last year is not valid anymore because there are too many things that change in between in the process, and that's often called a variance shift. The basis is not the same again. Then there are methods to compensate a little bit these drifts, but not always possible. Probably then you have to take new data. Sometimes if the process is not